The second half of Chapter 9 is about tests for homogeneity and independence. We'll start with homogeneity, but actually they're very similar, and I'll try to make that clear when we get to independence tests. So starting here with homogeneity, this is like an R-fold upgrade of the multinomial or goodness of fit test from part A. Or you can think about it as, R populations and C classes instead of one population and C classes or categories. Or if you want, you can think about it as a classification ANOVA. Remember, ANOVA is this idea from chapter 6, but in chapter 6 it's about Gaussian distributions, and here we're breaking things down into categories. The way that data is represented is in a contingency table, in particular an R by C contingency table. So C for columns, R for rows, and I cheated a little bit. I have copied the table from the book because it was just too much to write down and I knew I would make mistakes. So we have these R populations and C classes, and then we have double indexing for the observations that reside in each row and column. And then we have totals across the rows, so that's sort of new notation, N1, N2 up to NR and so on. And then we have this same sort of, I guess if you're looking across the bottom total row, that's like its own 1 by C contingency table with the sum of the observations from each column. We're going to come back to this table in a moment, but the want to know for a test of homogeneity is if each population, which is what you're looking at across down the rows, has the same classification or categorical probabilities or not. In other words, are these probabilities heterogeneous across the rows, or are they homogeneous? They all have the same probabilities. So if you were to write that out formally, you'd have that the observations only depend on the column and not on the row. Or the alternative is that some k not equal to j has pij not equal to pkj. So there's one row where a particular column has a different probability compared to some other row. Like in the goodness of fit test, each row size is fixed by the data collection or by the design of the experiment, but each column total, because the observations themselves are random, so these are the column sums, is random. And also note that the grand total, which you can get by summing the columns or summing the rows, is the same, and we call that n. Or in the code, I write n-TOT, just to be super clear about what's what. Okay, so before I tell you about how we go about doing the test, let me tell you about what's different when we're doing an independence test. So I'm going to change color here to red, and you'll see why in a second. So independence tests are subtly different. Okay, so in an independence test, we have a very similar table. So I'm going to go back to the table here, but we don't have different populations. We have kind of a column class and a row class. So this is just right, row and row and row. And this is going to be an independence table now. And this is going to be a column class. So it's like there's two classifications. So there's just one population, one pop, and then we have row class and column class. Both random. And we use notation R1 for the row totals and R2 and so on, R. Okay, in the book there are two different tables for this, but I thought it might be fun here to just try to show you in red what's different about the independence table. So we have one population, two classifications, a row classification and a column classification. I'm going to switch back to black here because I think that looks better, but I'm really talking about independence tests. So the want to know is if the row and column classifications are independent of one another. So that's the null hypothesis, is that they're independent or not. And that's the alternative hypothesis. What does independent mean in this context? It means, does knowing a row class determine or help you determine, probabilistically speaking, the column class, or vice versa? Okay. The model for both, so we'll put model in quotes for both. What do I mean by for both? Now I'm talking about both homogeneity and independence. So now we're going to kind of getting back to what they have in common is the same multinomial as for the goodness of fit test, but now this P is a matrix. It's an R by C matrix. In the case of homogeneity, the probabilities are Ni over N times Ci over N, or, so this is for homogeneity. And then for independence, we really have the same formula, but we use different notation. So this is independence. They're the same calculation, operationally speaking, because they would involve the same numbers if you set up the table in the same way, but just slightly different notation. And of course, I like to be a little pedantic. I goes from 1 up to R, and J goes from 1 up to C. I know this is confusing, but I think it's all going to make sense when we get to the examples. Gosh, I hope so, right? Okay, we know that the expectations, just kind of upgrading what we had from before, are n times those probabilities, which is going to be Ni times Ci over N for homogeneity, or Ri times Ci over n for independence. So let's just, we can keep kind of this going here just to keep it all straight. And then we're going to call that Eij. So this is Eij. So that the test statistic is a double sum upgrade of the goodness of fit one from part A. So just to write it all out, it's going to be sum Oij minus Eij squared over Eij. I equals 1 up to R, J equals 1 up to C. And I'll show you how to do the simulation, but again, I'm going to skip ahead so we can just avoid flip-flopping back and forth. You can show, using a central limit theorem like argument, that the distribution of this statistic is chi-squared with R minus 1 times C minus 1 degrees of freedom as n goes to infinity. So you can see that the two tests are very similar. You think about things a little differently, but operationally they involve pretty much all the same calculations, and asymptotically they have the same distribution. But because they treat randomness differently, to do it in a non-asymptotic way, say by simulation, involves a slightly different sampling regime. And I will show that to you. So let's pop over to R and do our first example. I'm going to do one example each, first of the homogeneity test, and then for the independence test. So these data make a table that is about job satisfaction for different amounts of time or seniority in the position. So this O makes a table that I can just show you. Across the rows is seniority. We don't think of seniority as random, right? When you ask a person how old they are, they don't misremember. And if you look at an employee base from one year to the next, it's not going to be random who falls into these different age categories. However, their satisfaction with their job or their reporting of their satisfaction could be modeled as random. It could be different depending on whether they're having a bad day or not, or a really great day, or something else happened in their life that has nothing to do with their job. So this is a situation where we have different populations of different ages across the rows and different classifications of happiness for a total of n, I call this n tot, a total of 258 employees. Okay, so let's extract row and column information for this table. This is, some of the stuff that I'm doing here is necessary and some isn't. We are going to need the n vectors. So these are the sums across the rows. So row sum is n, sums, should be sums. Okay, and then C is call sums O. And then the total we just did, but n tot could also be the sum of the C's or the sum of the N's, and that should be the same number that we got by summing up all the O's. I like to make a pretty table that looks like the one from the book, that looks like this one. It's not strictly necessary, but it helps me stay organized. So I'm going to put the column sums on the last column, and then I'm going to put, I just did that. No, I did that. Right? I put the column sums on the last row, sorry. And then I'm going to do the row sums on the last column. but I'm going to combine with that the total. Okay, so now I've got a table that has an extra row and column, but I don't have a name for that column. So I'm going to fix that. Call names tab. Okay, oh, that one should be N, and then row names tab is C row names O. Okay, so that should look better now. I've got all the row names and the column names correct. Then calculate the expectations. So going back to here, the expectations are calculated through the probabilities. The probabilities are up at the top, the expectations are on the bottom, but you can see we can calculate the expectations without first directly calculating the probabilities. So I'm going to make a matrix to store those and those expectations should be the same dimension of the original observations. So I'm just iterating over the rows and columns, and then I'm going to follow the formula for EIJ, which, looking at the whiteboard on the right, is Ni times Cj divided by N tot. So if I didn't make any mistakes, that should do it for me. So my expected table is that, and my observed table is that, and our test statistic is going to make a comparison between those two. So test stat. So I'm going to sum observed minus expected, square them, and divide by expected. So this is exactly the same formula as in part A, but now it's vectorized over matrices, or matricized if you want, and that's our chi-squared statistic. One other thing before we go to simulation, we don't need the double for loop from above, because you can get the same thing if you do what's called an outer product. This is like a really fancy thing that you can do if you want to impress your friends. So EFAST is outer n C over n tot. So this is making a product between the n vector and the c vector divided by n total. It's following this, and outer is getting you all of the combinations. So it's called an outer product. And you can check that EFAST is the same as E. So you can get it with one line using an outer product. That can be helpful if you just want to have a shorter, easier to read code. Okay, how do we do the simulation? Okay, so I want you to always baby steps, right? I'm going to have to take some sample of rows. So I'm thinking about this sample. I'm going to do a total of n tot samples. The probabilities are not going to depend on the rows, so they're just going to be the column probabilities. So I'm thinking about this like a multinomial. I would accumulate across the rows to get the column totals, dividing by the grand total, and then that would allow me to do a sample of the right total number in each row. And I got to have replace equals false, because this is a big toss of a die. I'm tossing the die across each one of the columns, just like in a goodness of fit test, but now I've got rows, but my null hypothesis says the row probabilities are all the same across calls. Okay, so that's how I could generate, whoops, I've got some kind of mistake here. N-tote, probability is C, length of C. What is the length of C? 5, N-tote. Oh, I mean replace equals true. I don't know what I'm thinking. Okay, so this gives me a sample that I just need to then arrange into a table, right? This has N-tote, and I just need to interpret that across the rows of the table. So I have to make another set of indices that helps me map that. So a mapping from a vector into rows, I can get that by writing the n's down as rep 1 to length n of n, and then I can do then combine rows and columns with the table command. So I can do table, take the n's, and then this let's call this C's, and I got to save that so then I can put it in here. Okay, I think that'll give me the table that I'm looking for. If you want to be really careful, there's a possibility that when you do a sample like this, that you never get any 3s. I just picked 3 arbitrarily, or that you never get any 5s. It's not going to happen usually, but it's possible, since you're doing things randomly, that you would miss some of the categories in your sample. So if that happens, you can protect against that by doing factor and telling it that this sample is supposed to have levels that go 1 to the length of C. Okay, that doesn't change the, oops, I'm missing a parentheses. That doesn't change anything in this case. It looks exactly the same, but if you ever get any warning that you're missing some categories in your sample, you can fix that by telling it what the levels of the factor are that you expect. Okay, so these would be our random observations. And now all we've got to do is put that in a for loop. So for I in 1 to n. Okay, I know that I'm reusing I, right? I used I up here, and I'm using it again, but I'm not going to need it in another for loop because I'm going to use the outer product in order to calculate my expectations quickly. So I won't need to worry about the indexing there. So here, I'm going to grab this. This is sampling my columns. And then I'm going to grab this. This is giving me the observations. And then I'm going to grab this outer product, which I'm going to upgrade to use our n's, row sums of OS. Those are the n's. And then call sums, those are the c's, divided by n total. And then I can calculate the chi-squared statistic as sum of OS minus ES divided by ES. I better square it. Okay, so I think that follows the multinomial sampling, the building of the table of simulated or virtual observations, the calculations of expectations with the row and sum totals that come from the random observations and the test statistic. Oops, I was trying to use the n I had before, but 100,000 is what we had before. Okay, call sums, I, as usual, messed up. Why is this not an array of, oh, because it's not, it's called, there's my mistake. I've got to use the full matrix. Yeah, that's right. X2 not found, X2S, and I better do X2S rep NaN. Okay. This could be a little pokey because I've got a big loop and some samples of 200 or so things, but it's done already. So now I just need to visualize that. The visual is not essential, and I know you can't see it yet, but there it is. And then AB line V equals x2, col equals 2. So I don't think we're going to reject this null hypothesis, but we can calculate a p-value. Oh, okay. This can happen. So why is it that we're getting some NAs here? So summary x2s. So most of the values are numeric, but one of them came back as an NA. Why does that happen? That can happen if you end up with an expectation that is infinite, which can happen when your outer product involves a combination that doesn't have all of the levels of a factor. So you can just say NARM equals true, and then it will ignore that 1, 0 that happened in the denominator of the expectation. And of course you can compare to the math. So that's PCHISQ x2. What is this? I got to get the number of rows and columns, right? So n row of O minus 1 times n col of O minus 1 lower tail equals false. Basically the same number. So I think it's kind of obvious that this is easier, right? But this is also not easy to comprehend. Like, why is that right? I told you it's because of like a central limit theorem type argument. But it's nice to know that you can virtualize the situation with sampling and get the same p-value. So we would fail, I'll write it down here, fail to reject the null hypothesis and determine that happiness is the same across age. In other words, the probabilities are homogeneous, which is why this is called a test for homogeneity. I said we were going to do 2 examples, so let's go to example 2, which is going to be for independence. And so I'm going to introduce a new data set. This data set you will have to download from the book webpage. Okay, so as long as you're in the same directory as this file, as long as your current working directory is the same as the code and you have the data in the same directory that you downloaded from the webpage, that should work for you. This data set has a lot of information in it. We're not going to work with all of it, but each row is a record of a police report for an assault in a particular time at a particular location, whether the victim went to the ER or not, whether police were called to the scene or not, the age of the person, their gender, whether the perpetrator was a stranger to them, and so on. We're not going to look at all the data. We're just going to make a table of observations that come from 2 of the columns. So we're going to use locale and income. Okay, so this is a very simple table. It's a 3x4 table that is telling you that there were 367 victims in a rural location who made less than $50,000 a year. And there were 839 victims of a crime that happened in a suburban area involving a victim that made between $50,000 and $75,000 a year in the late 90s. Okay, this is this would be a test for independence, not homogeneity, because both rows and cols are random, right? Think about how this might happen. Somebody is walking in a neighborhood at night, and you know, where they're walking, they could be walking anywhere. They could be in their own neighborhood, they could be in an unfamiliar neighborhood, maybe they're coming home from dinner or something like that. And where the crime happens is uncertain. It could be anywhere. It could be rural, suburban, or urban. And of course, how much the person makes, the person who's perpetrating the crime probably doesn't know what their income is. So it's worthwhile to ask if there's any relationship between these two things, or are they independent of one another. Okay. However, a lot of the operations are the same no matter what we are looking at. And I want to do a quick thing here. If you notice, these are not in order, and it's not important to order them, but I don't know, maybe I'm obsessive compulsive. I'm going to put them in order. So I would take the first one, and then the third one, and then the fourth one, and then the second one. And I think that would put those incomes in order. So I'm going to look at it that way. So extract row col info. So R is the row sums, and C is the col sums. And then n tot is the sum of everything, or just the sum of the R's or the C's. It doesn't really matter. And then I can build the table. Oh, tab. Oops, I better do that again. Okay. Okay, so now I've got the table, but I got to give it the correct row and column names. And rather than type all that, I'm just going to go find it, because there it is. Again, none of this building of this table is useful for anything, except I like to just check that everything looks like one of the tables that I have in the notes. Okay, now I can calculate the test statistic. So E is going to be outer R C over n tot. So I'm borrowing the fast one and skipping the double for loop, outer. And then the chi-squared statistic is sum O minus E squared over E. Okay. And now to simulate, well, first I can grab the columns from before. Right, so this is how I simulate columns. That doesn't change. But now I need to I need to acknowledge that the rows are also random. So I need to do the same thing for the rows, but I better get everything flipped. Right, so that should give me the rows. Now I can borrow the simulation loop that we had up here. Whoops. I guess I didn't do anything with that, so I would have to take this, just to kind of complete the train of thought here, by doing the row here, and I could do the same factor thing just in case. That might not be necessary. Okay, and then that gives me a random table, which I then compare to the observed table. Okay, so now the full simulation, I better grab all of this and then just put it in here. I'll put a new line here because that kind of looks gross. And then everything else I think is the same. So it's going to go. And it could be a little slow because I'm doing a little more sampling. But the visualization is going to be the same once it's ready. And AB line V equals x2, call equals 2. I don't remember how long this takes, but I don't think it takes more than a minute. So if it does, oh, there it goes. It's done. And then we can put the line on there. Oops, why does the line? Oh, because the line is off the screen. So let's do xlim equals 0 to x2. I better put a C. I remember now that it's way off the screen. So this is an easy reject, right? Easy reject of the null hypothesis. Because the p-value is basically 0. You could do mean of x2s bigger than x2, but it's going to tell you 0 because none of those samples are to the right of the red line. And if you do it the math way, with PCHISQ, x2 n row of O minus 1 times n call of O minus 1, lower tail equals false, you can get a kind of more precise number, but I mean, not really. 1 times 10 to the minus 55, your computer doesn't even have the ability to represent a number that's as small as 10 to the minus 55. So that might as well be 0. So this is numerically 0. Put that in a comment. All right, so that's not goodness of fit. That's test for homogeneity and independence. And now you know 3 kinds of Pearson chi-squared tests.